In this lecture, I am going to introduce you to the concept of meshing. So, what is meshing? The process of converting a geometric model like this into a FE model like this, which contains discrete nodes and elements, is known as meshing. The process is known as meshing. Coming to the element types used for meshing, there are 1D elements, 2D elements, 3D elements, and other elements. So coming to 1D elements, where are we going to use such type of elements? So when we take a geometry where one direction or one dimension is very large in compared to other two dimensions, then we can assume or we can mesh that particular geometry with 1D elements. So see here, one of the dimension is very large in comparison to the other two dimensions. So the element shape is in the form of a line, and we need to be providing the other two dimensions in the form of a cross section to this particular element. And coming to the element types, let us say 1D element types, they are rod element, bar element, beam element, pipe element, axisymmetric shell element. So these are all examples of 1D elements. And in practical applications, when we have long shafts, beams, frame structures, pins, and other sorts of structures, we may use these 1D elements to mesh them. Then coming to the next one is the 2D. So here when two dimensions are much larger when comparison to the third dimension. So for example, here in the plate, what happens, this length and width of this particular plate are very large in comparison with the thickness of this particular plate. So what we are going to do is we are going to use the 2D elements to mesh such type of geometries. So here the element shapes used is the quad elements and the triangular elements. And we need to provide the remaining dimension, which is nothing but the thickness dimension, to this element. And here the element types are thin shell, plate, membrane, plane stress, plane strain, axisymmetric solid, etc. are the type of 2D elements available. And in practical cases where we are going to analyze the sheet metal parts and plastic components with very minimum wall thickness, we are going to use the 2D elements in order to mesh such type of geometries. Then coming to the 3D, so if you have all dimensions with comparable values, then you can say it is a 3D object, and if it is possible, you can idealize this 3D as this 2D, or otherwise you can also idealize this 3D as 1D. For example, let us take the shaft. It may be a 3D, but you can simplify that particular shaft geometry into 1D to decrease the analysis time, analysis resources requirement, and analysis. The element shapes available for 3D are tetrahedral, hexahedral, pyramid, and other sorts of elements. Then there is no additional data you need to give for the element in order to perform the analysis. Then you come to the element type. It is a solid element type, and practical applications are where there is a solid body, you are going to use this particular 3D element, like say it may be a transmission, engine block, crankshafts, etc. And as I've told you, we can, wherever it is possible, we are going to idealize this 3D or simplify this 3D and make it as a 1D or 2D. And other sorts of elements exist like mass element, spring element, damper element, gap element, rigid element. So these are all different elements that are used to say simulate either mass, simulate the stiffness of a spring, or simulate the spot weld and other sorts of things. Then how do you select the type of element that you are going to use for meshing? So it is based upon three major factors. One is the geometry, size and shape, then type of analysis, and time allotted for the project. So coming to the first one, type of geometry. So depending on the type of geometry, you are going to select the 1D elements. Here is an example of a body where this length is 1000 mm, but the dimensions width and height are 10 into 5. So what happens, this 10 and 5 are very less when compared to this length. So such type of geometries can be idealized with this 1D elements. So for example, see here, there is a long shaft. This particular shafts can be analyzed using this 1D elements. Likewise, if you have frames, steel frames or steel structures like this, you can idealize them in the form of a 1D beam, and you can analyze using 1D elements only. Then coming to the second one, here see the dimension, length dimension is 500 and the width dimension is 300, but the thickness is 2. So what happens when compared with the length and the width of this particular structure, the thickness is too low, And see here, we are going to use the 2D elements in such type of geometry cases. These are the shapes of different 2D elements that we generally use, and these particular elements are available with every software, FEA software. Then coming to the application, see here we have an airframe where this particular total structure will be simplified as a surface, and analysis will be done by meshing this total geometry with 2D elements like shell elements. Then here is an example of a computer rack, sheet metal rack, which can be analyzed using 2D elements. Then coming to 3D elements, when all the dimensions of this particular body are comparable, then we will be using 3D elements. See, these are the different shapes of the 3D elements available. And here some of the examples of this 3D element modeling include like this transmission systems and this type of coupling systems and other sorts of systems. As I mentioned earlier also, if there is a possibility of simplification, we are going to use that simplification of 3D objects into either 2D or 1D, and then only we are going to perform analysis. So based on the geometry, you need to select what type of elements that you are going to use for meshing. And then the next one is the type of analysis. Say, based on the type of analysis you are doing, you need to select the type of element. For example, if you take the structural and fatigue analysis, if you come to 2D, the quad elements, if it is come to 3D, hexahedral elements are preferred over other type of elements because of the accuracy they give for the solution. If you come for the crash and nonlinear analysis, what happens? Priority to mesh flow lines and brick elements are given over the tetrahedron elements in order to get accurate results. Likewise, depending on the type of analysis, say for example, if you are performing mold flow analysis, then instead of all other elements, triangular elements are more preferred over the quadrilateral elements. So coming to the dynamic analysis, and depending on the type of geometry also, we have lots of types of elements that can be selected. Then coming to the final factor is the time allotted for the project. So for every project there will be some time. Based on the time, you can just use the automatic mesh generation tools, or otherwise you can also do manual meshing by setting up every mesh control, and you can check for this mesh. Automatic or batch meshing tools could be used instead of time consuming but structured, good quality providing methods. Then for 3D meshing, tetras are preferred over hexas. So what happens is, if you are going to put up hexas, the solution time will be more. So that is why if you want to reduce the time of the project, you need not have a lot of concern over accuracy, you can then go for the tetras. And there are other lot of factors which are included again into this particular time allotted for the project. So based upon all of these factors, you need to decide what type of element you are going to use, what type of settings you are going to use, how are you going to generate the mesh, are you going to generate the mesh manually, are you going to generate the mesh automatically, and there are other lot of factors you can select. So coming to the question, can we solve the same problem in different ways? Yes, we can solve the same problem in different ways. Here for example, we have taken a fixed beam where we have solved this particular beam in the 1D form as well as in the 2D form as well as in the 3D form. See here, coming to the 3D form, what happens? The number of equations to be solved was 52,344. Then coming to the 2D, what happens? The total equations to be solved are 54. So what happened? Around 10 times less. So the number of equations that are to be solved here are 10 times less when compared to the number of equations that are to be solved in this 3D case for the same problem. Remember, this is for the same problem. Likewise, coming to this 1D, so what happens? We have only 12 equations to solve. So this is much better. And remember, if we are going to follow everything, we are going to get the same result, approximately same result in the 3 cases. So what happens when there is a possibility? You need to take some assumptions and you need to simplify your geometry from 3D to 2D, and if it is possible, you need to change it from 2D to 1D as well. So we can solve a same problem in different ways. Then finally, what are different meshing steps? So first thing is, you need to sufficiently understand the geometry. So what are the features that are present in the geometry? How can I mesh this particular geometries? How can I say use the different settings to accurately convert each feature? For example, let us say if you have a straight face, it is easier to mesh when compared with the circular face. So you need to study the geometry, and once you study the geometry, you need to estimate the time. So you need to estimate the time of generation of the mesh as well as time to solve the particular problem, and what is the accuracy required also you need to keep in mind. So depending on the accuracy required, you need to perform the time estimation. Then coming to the third step, we are going to have to check the geometry. So once we are going to import the geometry from other CAD systems, we need to check whether during the transfer process are there any losses that are created, or is there any data loss that has occurred. Then fourth one is symmetric check. As I have told you, we need to say decrease the size of the model in order to increase the efficiency of the problem. Then for that purpose you can do symmetric check, and if there is symmetry in the object, you can decrease the size of this particular model. And then you need to select the type of elements that you are going to mesh the object with, and you also have to set the mesh settings. So what happens is there are number of mesh settings like selection of edge length, selection of different types of elements, different types of methods to say mesh the geometry, and other lot of settings are there. You need to master all those settings, and you need to select all those settings. And once you selected all those things, then final thing is you need to select the contact meshes, and you need to model the joints. And once you have done all these things, you can generate the mesh. So these are some of the steps that are followed in the industry while performing a mesh. And once you are satisfied with all these steps, you can just go and just generate the mesh and send it to the FEA engineer. In the next lecture, we are going to see some of the global mesh controls that are present, which are very useful in generating mesh inside ANSYS Workbench.